Let's introduce our speaker today. It's Dr. Behrokh Beiranvand. Sorry if I pronounce his name correctly. He finished a master degree in Iran and Islamic University, and he got PhD in Moscow Institute of Physical Technology, and the same like Andrei finished. And okay, he's talked today about Telegram detector arrays, and yeah, let's welcome, welcome. Now we can start.
Okay. Thank you for your invitation and for your introduction. Sorry it was for reflection if there was some error in understanding. Today I'm gonna talk about development of metamaterial-based optical and Terahertz detector arrays, which we worked on at MIPT, and it's my pleasure to present this topic with you. Here I'm going to talk about create and study distributed structure for detection Terahertz radiation and some optical radiation. This structure, they can be 1, 2D, which they are consist periodically translated unit cell, and we can confine electrodynamic properties. And you know, we work and we design this absorber because it's easy to integrate with optics. Large aperture can be filled with these detectors and increase dynamic range, and also multi-octave bandwidth is possible by these designs. The topics I'm going to talk about here is our goal. A little bit I will talk about Nis and Sinis junction, which invented by Professor Leonid Kazmin already. And after that, I start our design based on metamaterial array for called electron bolometers. And the another design which it can be interesting for you, it was about composite right left-hand transmission line based on thermocouples and local field enhancement boundary states and graphene plasmonic absorber, which I think it can be interesting to talk about. Here our goals were arrays of planar antennas with integrated Sinis junctions or bolometers for radio astronomy research, and development of an integrated circuit for Terahertz radiation. Also increase the Raman scattering cross section using edge effect in a photonic crystal. It was another goal, and design to enable plasmonic absorbers based on layer of graphene for one based on 1 and 2 resonator. It's another approach. So let's talk about the first slide. I'm talking about Nis and Sinis junction. As all of us know, it's a junction of normal isolator superconductor, which you can see at the left side, and it's a basic schematic I'm talking about. And you know, by applying voltage, the Fermi level of normal metal will be above the superconducting, and through the isolator we've got the tunneling process. So but in fact we use 2 junction by add another isolator, as you can see in the right side, and superconductor, and add this voltage in order to have better design and also the 2 cooling process. Let's talk about our designs at MIPT. Here we try to modify the previous design, which before me it was done at Chalmers University, and there they design frequency selective surface, which there it was a large unit cells, and these large unit cells only absorb, as I remember, maybe around 10%. And our goal here was to increase the bandwidth of absorption here. So we worked on a small size unit cell. As you see here, it was the first design which we started with, And here we work at the frequency 250 gigahertz. As you see here, it's a unit cell of a frequency selective surface, which this arrows can show you the sinus junction, and which we integrated it into this antenna, and we designed our bolometer, and we used this frequency selective surface, or FSS, as bolometers here based on this integrated sinus junction. In the middle, you can see the lump element equivalent schematic based on vacuum and impedance of vacuum, impedance of frequency selective surface, and the substrate, which is silicon. Based on this curve that you can see is a function of power absorption as a function of impedance of frequency selective surfaces. Here at the vacuum side, we do not have any short circuit boundaries, and so we measure it here, and we saw that around 80 ohm we achieved the maximum power of absorption for this design. And it was the first step which we sought to modify the structures, and we saw that the absorption is increased. But let's talk about this wire that you can see. They are very important because the effect on results a lot we face with. Let's now talk about the modes. We have two modes in order to absorption, and when E field is in Y direction, and when E field, electric field, is in X direction. So as you see, the absorption and the impedance here for each adjacent unit cell, if when you have that two wire that I show you, the capacitance between the two unit cell can be tuned out because of this DC wire that I show you. And here it's the impedance imaginary part can be zero. So only in one mode we face the maximum of absorption. And for another mode, as you see, we couldn't tune out the adjacent capacitance of each unit cell. So in the middle, you can see for mode 1, we have the maximum absorption, but it's a function and K vector angle, as you see here, and until around, as I remember, 15 degree, we have the maximum absorption. Here also we have some absorption, but this is not useful for us. And also you can see the experimental setup as a schematic. You can see here is a schematic of experimental setup and our backward wave oscillator of FSS and sample holder. And this is the sample that we fabricated. Here it's this result were measured by Michael Trosov from IREE. And Dr. Michael Trosov measure this VI curves and our experimental result there. And as you see at the our target frequency, because you know, we have a lot of modes and a lot of maybe unwanted signals in experimental for external circuits. And a lot of modes in black body, as you know. Here at the target frequency, it's not the smooth, but we observe the results. And in the middle, you can see a function of temperature of black body and the response of the structure based on microvolt that you can see has inverse design, which the black body temperature is increased, the result will decrease, and it's the same for positive and negative side. And also it's volt ampere characteristic, which you can see is as a dynamic resistance. And also we can see IV curve here. It's was measured for this sample. But we try to again modify this structure for another mode we faced that this DC wire, they are very important in the previous design, and we add 2 wire also in X mode or X direction for electric field. And here is already small. If you see it, here is integrated 2 bolometer in figure B. The 2 bolometer are integrated, but in figure A, it was the same structure that I show you, but I add here silicon layer in order to increase again the bandwidth, and I add a DC wire on another direction, and you can see the fabrication pictures which you can see here, and this is the junction. Let's see what will happen if we add this wire and another modes. If you see the absorption, this is for figure A that I show you, the smaller ring. You can see we have in both mode we have wide range of absorption, and if we can calculate if both absorption in mode 1 and mode 1 and mode 2 based on the data. You can see if by see this simple equation, we can measure the arbitrary absorption as a wide band for both modes. So we observe that the DC wire, they are very important for each mode absorption. For the another design, which with larger ring that you can see, because it was the same and symmetric, we have the same absorption for both modes, which we calculated the arbitrary power of absorption. We observe the same, and we switch to another design. Here it's in fact it's 2 of frequency selective surface, which they design on one only one substrate in order to work in both frequency for radio astronomy around 210 and 240. It's a dual mode and excuse me, double band frequency selective surface, which again we try to integrate it. We have here integrated 8 cold electron bolometer or Senes junction, and here we have a back short which if we design an equivalent circuit here, it works for us as a short circuit, and the radiation is from substrate side, and we have each FSS on one only substrate. We can receive 2 frequencies simultaneously. So but here there is some problem which we are working on. It was here I designed a bridge because I didn't want to connect this 2 frequency selective surface and bolometers together. But this bridge, again, it works as a capacitance, and unfortunately here I observe at this frequency, lower frequency, I observe the unwanted absorption, and it worked as a interference for me. And here I resolve this problem for higher frequency. Here I have some noise that from another bolometer, which I'm working on to remove this unwanted frequency. After that, it can be fabricated. It was another design which we finished, and I think it's not fabricated yet. It's numerically only. Here we work on a large unit cell. Until now, I talk about the small unit cell size. Here we design large unit cell size, but before this design, they had, as I said, they had a small range of absorption and small bandwidth. So we wanted to increase this absorption for the large unit cell. And so the first step that we finished, it was the, as you see into the inside of as a shadow in this picture, here we remove the unit cell which before they are designed. And because of dynamic range and reduce the number of this bolometer, and we 4 times from this blue curve that you can see here, the total NEP it was modified around 4 times, as you see here, and it was the first step that we done. But again, the problem was that the bandwidth, we wanted to increase it more, around 20% or more. So we tried to again to reduce the number of the bolometers. So we designed an asymmetric antennas for this bolometers, and here we integrated it on each in each large size unit cell, which are asymmetric at the target frequency that we work on for it for small size of unit cell. So, but here the size of unit cell is large, and let's see what will happen and what we observe. Here you can see the radiation coming from the substrate side, and here we have a back short circuit for boundary, and you can see the schematic as a transmission line. As a transmission line and equivalent circuit, here we could measure impedance of substrate and impedance of back short, which here we have the vacuum impedance, which is shorted here by this back short boundary, and it is our frequency selective surface, which in a previous design I show you, and it's asymmetric. And this curve is important for etching and fabrication, because we know at the target frequency we can see the function of impedance of substrate and impedance of back short section of this design, or back short part of this design. And for the final result can be observed here. The frequency selective surface, we can see it's not the same, but fortunately, the absorption also at the band, large bandwidth, more than previous design, they are the same. So we have a design which is not symmetry, but the result at the target frequency is symmetry, and we increase the bandwidth. And here, if you see as a function of cosinus, you can see the power of absorption also is the symmetry, and for around 20 degrees, which for all input telescope, it was our task to have absorption. We can see the symmetry results. It was interesting for us because we increased the bandwidth of absorption, and also the result base of power absorption was the same for both modes. And but the design is a large size and is not symmetric. So it was the cold electron bolometer design which I finished. A little bit, I want to very quick talk about another design which I done. Here it's an array of thermocouples that you can see for this transmission line. It was based on composite right left hand transmission line and with no DC connection. Here, if you by a laser, as you see, but you eliminated thermocouples, you have voltage on two different metals, on two sides of different metals. You can measure voltage if you excite it based on the Seebeck constant equation that you can see here. So we use this Seebeck constant, but these thermocouples are set on a transmission line composite right left hand, and if you eliminated this design, you can measure the we can say maybe by picosecond laser. If you measure it, you can measure the Terahertz voltage pulses. I designed here the composite right left hand transmission line. I designed for that an equivalent circuit, but here I have no this inductance because the same magnetic field is around each thermocouple around this transmission line, and as a function of frequency, each elements were calculated, and the wave vector show us that the speed of this work, which we can see is work as a hybrid transmission line exactly at the I think around 25 gigahertz. So also I measured by eigen mode this structure, and I measured the power calculated, and I observed that 0.17 microwatt, which show us the phase velocity exactly at the frequency that we have the K vector, and the group velocity maybe can be interesting for us. Also, we can observe the electric field distribution here that can sit on the surface of which the thermocouple are designed. Another design which we finished, and it was interesting for us, it worked p-polarization as polarization for plasmonic crystal, which we measured for both mode each unit cell as a honeycomb that you can see. Two probes are installed here. We try to design is as it work as a edge a state plasmonic crystal, and we wanted to direct the electric field in the middle. And if you see here, we design a gap here, and we try to see the electric field exactly at this direction in order to detection the frequency, and we modify the enhancement factor 12 times. So also it was designed for a green laser. It was interesting, and as you see here in the green laser, the structure, it was designed based on unit cell, and we add some probes to measure the electric field on the surface of this structure. Enhancement factor was measured, and it was the same, and for each probe which we make a distance from the gap which I showed you, you can see the electric field enhancement decrease. So the maximum of electric field enhancement, it was in the gap which we designed for this structure. And it was the final result which we observed, and on the green laser we observed this result exactly. It was around 550 towards it was our measurements. Next design, it was interesting also. Before, a lot of people, they work on absorber of plasmonic absorber, but here we try to design a absorber, but which can, as you see, it has 100 absorption, but here we try to make it tunable. First, we design an elliptical shape into this structure. In elliptical shape help us to divide it in two resonators, as you see here. But by add a layer of graphene here, we have two peaks which separated, they are tunable for absorption. And if you see the result of based on the potential, you can see each peak of absorption is separately can be tunable based on as a function of potential of graphene, but separately, as you see here. And we modify also the absorption at this frequency from 2 to 2.33% to, as you see, around 15 and 20%, as I remember, for each peak. And we use this equation to tune each potential of unit cell for each resonator. It is the same design, but it was not elliptical. We wanted to test it on two resonators, which they are separated in the design. And as you see here, again, we have to pick which by graphene it can be tunable. But again, the interesting is not the jumping in absorption. The interesting, it was each peak can be tuned separately again, and on another frequency we observe the same results. So it shows us that by plasmonic we can tune the different type of resonator on one only structure. Here it was the all the detectors which we designed, and based on this design, as you saw, we try to design ultra wideband of 2D arrays of cold electron bolometer for sub-wavelength unit cell size. And here we absorb more than 70% of incident waves. Also, in another design, as we showed you, that it can work at 2 frequency, and it work at dual band layer, which based on periodically array of cold electron bolometers I showed you, which is not fabricated yet. It will be after fix this unwanted signals, unwanted results. And I show you a hybrid transmission line also with anomalous dispersion and hyperlight phase velocity, which the purpose of this design, it was measure the voltage based on femtosecond laser of light, and we can generate TRAS radiation. And the design I talk about, it was edge state plasmonic with 4 layers, plasmonic layer crystal, which we can increase the partial factor and quantum dots, and which at the end I showed you 2 tapes of plasmonic based on absorber based on the graphene, which each one are separately tunable. My time is yours if you have any question.
There's some question.
What equipment do you use to detect these frequencies?
Which frequency, which cold electron bolometer talking about?
Right, right.
Okay. To measure, the first step which we design this type of a structure, first numerically we design them by CST. And as I show you here, this is the experimental setup which for measure of this structure, it was some LNA and readout system like VNA and a spectrum measurement to measure the volt ampere characteristics, and it was the equipment which we use. This design, it's in 2 tapes we design it, numerically and experimentally. And numerically it was by CST, and experimentally it was based on cryogenic system, as you see here, into different temperature of Kelvin, also some readout system. But this readout system, it was wave spectrum measurement facilities like VNA and some LNA and GPA we use to measure the volt ampere characteristics.
Thank you.
You're welcome.
Yeah.
Can you go back to the slide 25?
Slide 25, yes? 25. Okay. This one?
Yes. So can
Okay.
you so you define data over here. Could you remind me what is the data? Theta.
The data.
Yeah.
Okay. Let's talk about let's come here from here first. This is our structure that you can see on A and B. Okay. Here, an elliptical shape. It was as a groove. It was designed in the silver.
Mm-hmm.
And here we have a dioxide of silicon, which this 2 tape of material made us a plasmonic structure. Here, this structure now I'm showing you, this results is without graphene, okay? It shows us 100% of absorption, as you see here. But this elliptical shape help you to have 2 peaks. Here also on the left side A, figure A, there is no, again, a graphene. If you have you rotate your design, or you rotate the eliminated radiation, and based on this angle, if you see in to this instant, you can divide the absorption as a two peak between these two resonator, as you see here in the E field at the wavelengths, two different wavelengths. And after that, we put a layer of graphene on the surface, and it is a red curve, as you see here, to increase your absorption from the without graphene structure and with graphene. And the red curve is with graphene. Now we test the potential of graphene, and based on this curve that you can see at the wavelengths which you have one peak maximum absorption and can be tunable, the another peak is fixed by change the potential of graphene. And for the other one peak, you can see when the other one is fixed, you can tune the another peak of absorption here. It was the main goal of this design, and the goal of the design, it was in fact this curve that you can see. At this frequency, the graphene has only 2.3% of absorption, and we try to increase this absorption more than 15%. So I don't know, you received your question.
Okay. Yeah, because of your this structure, you only see two peaks. If we have more, then you'll see more peaks.
Yes.
Right? Okay. Do you have any NEP measurement for this design?
No, EP, no. I measured this by absorption, only by numerically simulation CST, and I didn't. Yes.
Do you see any expectation in number and power?
What? Excuse me.
Any expected number?
No, I only absorbed the. I only measured the absorption, and I didn't calculate the power for this, because my goal was that for the next step to fabricate this structure, and all of them are postponed to experimental results.
I saw one of your slides show some NEP measurement. It's not the measurement, were your calculations?
Yes.
It's calculations.
Yes.
Oh, okay.
Yes, they are calculations. Okay. Yes, calculation of absorption.
I see. So which means that those numbers must be the minimum numbers, right? In reality, it's going to be higher.
If here the goal, it was an absorber, which the main goal, in fact, for Faraday rotator. I designed it to fabricate it to work as a filter or a modulator or absorber for this Faraday rotator. For that, I selected the elliptical shapes, and I want this structure work for us to enable at two frequency, but each frequency can work separately. For that, it was the main goal. Yes, the Faraday. Okay. For that only, I calculated the results.
Good, very good. Thank you. Okay, so what would be the technical challenge, to have this kind of design apply to much lower frequency, like a 10 gigahertz or something like that? You can still make this kind of structure.
Yes, we can design it, but let me talk about the frequency. Yeah. If we switch to lower frequency, the design is different because it's plasmonic structure and optical frequency. If we switch to another design, we can use elliptical shape. But for the lower frequency, or we have to design the structure based on that frequency. And maybe we couldn't use this material, but the structure, this elliptical shape, can be used, and the idea can be the same. Okay. The first idea, yes, right. We can switch to another.
So then the following question is, what would be the NEP behave with the low frequencies? Is it going to go up or go down?
Yes, we can work on the lower frequency, yes, but I didn't calculate it, but I can calculate it at lower frequency also. But at this frequency, because exactly my task was that design this absorber for at this frequency for Faraday rotators. It was my task on only set it on this at these frequencies. But your comment is interesting, which we can work on lower frequency based on this elliptical shape. We can switch to lower frequency with the new design was elliptical shape, and we can measure EMP. Yes, you're right. And thank you for your comments. If you're interested, we can keep going with another design.